Hello class and welcome back to our discussion on data. The second part of this introduction to data is looking at what types of associations can variables in our data set have. So there's going to be three main types of bivariate. And so when I say bivariate, I just mean two variables. So bi meaning two and variate meaning variables. So three main types of bivariate associations that we can have between variables. We can have numerical versus numerical. So we have two different numerical variables. We have categorical versus categorical. We have two different categorical variables. And then numerical versus categorical, which you guessed it, we have one numerical and one categorical variable. When we're looking at numerical, we're generally numerical versus numerical, this first one, we're generally going to think about it as a scatter plot. So we've all seen a scatter plot before where we have these, we have an x and a y axis. So we have our x and our y, and let me make that a little bit nicer. And we have our x and our y. And a good thing to keep in mind when we're talking about variables and an x and a y axis and plotting some points, we want to think about what we just learned in the last video, our explanatory variable and our response variable. Our explanatory variable will always be on our x-axis, and our response will always be on our y, because we want to see how a change in x also leads to a change in y. Those are going to be two important points that we're going to want to keep in mind here. I don't want to get rid of everything. Look at this. And so when we see a scatter plot, we're going to see all these points. And in this scatter plot, we can definitely see that there's a relationship between these two numerical variables. They kind of follow this line right here. So it looks like as x increases, so does our y variable. Now what about when we have two categorical variables? Now let's just do a simple example where we have category 1 on the top, and we have category 2 on the side. Now let's say that we have two different categories for category 1, and we have three different categories for category 2. Now let's assume that we have 50 people in each category for category 1. So we have 50 people in this column, and we also have 50 people in this column. So let's do this column as yellow. Color it all the way in. And then let's do this one as blue. So we have category 1, so we have people that maybe like to wear yellow, and we have people that like to wear blue, let's say. Now, if we didn't see any relationship between category 1 and category 2, then we would see a pretty uniform distribution. So if we have 50 people and there's three different categories, we would expect, I think it's going to be around 13. Can I do math on the fly here? I think it'd be about 13, or no, 16. Yeah, it's going to be about 16 per. So we have 16, that's 32, and then we need 18. So let me maybe make this 17 and 17. And then we'd also see about 16, 17, and 17 for our blue category. But if we see some sort of relationship, then we wouldn't see this normal distribution, this even distribution. We would see something like 5, 5, and then 40, and maybe 30, 10, and 10. Now we can clearly see that the breakup between people who like to wear yellow and people who like to wear blue, they have a very different response for category 2. So there's definitely an association between these two categories, and we can see it play out in this pivot table. We can also create a heat map, so we would maybe color in darker. So let me try, we could color in this darker. Let's try to do this. Whoops. Undo. So you can maybe make this one red and this one red. And then, so that would kind of highlight that those two are larger than the other cells in our pivot table. And that would be a way of visualizing how categoricals or categorical variables interact with each other in the form of a visual. Now the last one that we can look at is numerical versus categorical. And I'd say the easiest way to visualize this is we have our categories on our x-axis. I don't know how to spell, sorry. We have our cat, and we have our numerical. We might do different bars. So we have a bar here, bar here, bar here, bar here, and a bar here. So for these first three, we definitely don't see a whole lot different in our numerical variable versus our categorical. So we have 5 categories, and we're looking for the average of a certain numerical variable. But these two over here, we can definitely see that those 2 categories have a much higher average value than the other 3 categories that we have. So we can definitely see some sort of association with the categories in our data set if we look at it like this. Okay. And this is the type of, so when we see relationships like this, where we see a relationship between 2 numerical variables, 2 categorical variables, or a numerical and a categorical variable, we generally say that these variables are dependent on each other. So a change in one leads to a change in the other. So when we have an explanatory variable that leads to a change in our response variable, we can say that those relationships are dependent. The variables that exhibit a discernible or statistically significant pattern when one changes are dependent variables, but we might also have independent variables. And these are variables that do not exhibit any discernible change or pattern when one variable changes. And so how would that look when we have these type of relationships, but they're independent of each other? So again, we're going to draw a XY scatter, and we might see something like this, where there's no discernible trend in our X and our Y. It really kind of just doesn't look like there's any discernible trend in here. For our categorical versus categorical, I'm gonna see if I can grab this. I don't want to do that. Okay, it's okay. So I'm just going to draw it again. So we have our table again, where we have 2 categories. And let's do it the same, where we have one that is yellow and one that's blue. And we have the same scenario where we have 100 people total, and we have 50 per category. So we have a situation where we'd have like 16, 17, 17, and let's say 17, 17, 16. So there's no relationship. It doesn't really matter what category you are, whether you like to wear yellow or blue. It doesn't impact anything about this other category. Let's say this category 1. It doesn't impact where you fall in category 1. It's completely random. There's a completely even distribution among the 2 categories. And the same thing for our numerical versus categorical. We might have, let's say, 4 bars. And there's really no discernible difference between where those bars fall. We don't really see a whole lot of change when we look at our independent, or when we look at our 2 variables. When we see this, we tend to say that they are independent of each other. There's no association between our variables. The last part of this is looking at numerical associations, and we have what's called a positive and a negative correlation. So before we looked at an XY scatter plot, where we could have our X and our Y, and we had some positive correlation like this. where if we were to draw a line of best fit, it would look something like this. So we see as x increases, so does y. And then we would conversely have a negative correlation where we can expect that as x increases, we would see a decrease in our y. So if we draw a line of best fit here, it's going to look something like this. And so as x, x increases, our y decreases. And so when we say something, let's draw the x and a y here. So in the negative correlation, when there's an increase in x, we see a decrease in our y. And I also want to plot out one other thing. So I'm going to erase these for a second. And we're going to talk about this later on in the course as well. But one thing to keep in mind is that when we talk about positive or negative correlations, we strictly mean in the linear sense. And what do I mean by the linear sense? So in both of these scenarios, we can draw a line like we did here, and you can draw a line like we did here, that clearly show there is a positive correlation with, or positive or a negative correlation with our chart. But what happens if we do something like this? So we have x and y, and let's say that it seems to look like as x increases, so does our y. At a certain point, we start to see these dots go in a different direction. So actually, after you pass a certain point, we see a change, and our x's have a sharp decrease, or our y's have a sharp decrease, and then they kind of fade off like this. Now, we can say that a line generally follows this sort of pattern, but if we're describing it only in linear terms, then we can't really draw a line. So if we were to draw a line of best fit, it would look something like this. There wouldn't be a strong either positive or negative correlation here to detail, but we can definitely say there's an association with these variables. So when we talk about positive and negative correlations, we're strictly talking about linear correlations. How well can we draw a line with the data? When we have nonlinear correlations like this, so let me do that, nonlinear. When we have nonlinear correlations, then we have a harder time saying whether or not it's a positive or negative correlation, because it's not linear. We can't draw a line to do that. So that's this section talking about different types of associations and relationships we can have between our variables. In the next video, we're going to talk on some very basic principles on collecting data and how do we obtain useful data for our analyses. Thank you, and I'll see you in the next video.